Hello, so welcome to a video on electric fields. So in this video, we'll look at like summary of the main points that you need to remember in electric fields for A-level physics. So this is not an exhaustive list of points, but the main points that will help you remember the concept. Okay? So let's get started. By definition, an electric field is the space that surrounds electrically charged particles and in which a force is experienced. So a force is exerted on an object or a charged object that is placed in that field, which means when you have an electric field, if you bring a charge close to that field, that charge will experience a force, okay? And the electric field pattern between 2-point charges depends on their polarity. What does that mean? So it means that if the charge is positive, if the charge that we have is positive, then the electric field lines, if the charge is positive, the electric field lines will point away from the object. So let's say we have a positive charge, so the field lines, we have arrows that go that way. Okay, so that's what it means. And if the charge is negative, then they have the arrows that go inside like that. It's pointing towards the charge. Okay. I clear this. Okay. Then the field lines always point in a direction that a positive charge will move in a field, and an electron will move in the opposite direction, which means if you have a positive charge, so if you place a positive charge in the field created by a positive charge, so you have a charge that creates an electric field. If you bring another positive charge, so remember, there will be a repulsion. So that test charge that you bring will move away from that charge. So that is why the arrow will point away from that charge that creates the electric field. So you have a positive charge, and you're trying to bring another positive charge close to it. So this charge will repel, will be moving away from it. So that's why you will see that the arrow will point away. So the direction of the field is the direction in which a positive charge will move when placed in the field. So if you have a negative charge, you know, there will be an attraction. So that positive charge will move towards that negative charge that creates the field. Okay. Now, charge do not reside inside a conductor, and all the excess charge, whether positive or negative, rests on the surface, which means within a conductor, inside of that, the interior part of the conductor is neutral. So all the excess charges will reside on the surface of the conductor. Now, electric field lines. So let's look at properties of electric field lines. The electric field lines are imaginary lines that represent the presence of electric field in a region around charged particles. So the properties of the field lines include, so what are the properties of the field lines? So the arrow points away from positive charge and towards a negative charge. We will look at that. So the density of the charge of the field lines at a point represent its strength. So the density is related to the strength of the electric field. So which means if the field lines are close to each other, then we know that the strength, you know, if we have a negative charge, so, you know, you have something like that, and you have the field, you know, this is a radial field. So you have the field lines like that. So you see that so close to the charge, the field lines are closer to each other. So it means that the strength, the field is stronger around here, close to that charge, compared to when you move away from it. Okay. Then field lines never cross, as the crossing of field lines would represent, would indicate that the test charge at the intersection will experience two different forces at the same time, which is not possible. Okay. Field lines are straight and evenly spaced when you have a uniform field. And so when you have a uniform field, the field lines are straight. And for example, let's say you have two plates, and the two plates creates a uniform field. So these field lines will be evenly spaced and they will be straight. Okay. So if this is positive plate and this is negative plate. Okay. So that's what that property means. Now, the electric force between two charges is governed by the inverse square law. So, and it states that the magnitude of the force between 2 point charges in a vacuum is directly proportional to the product of the charges and inversely proportional to the square of the separation distance between them. So what that means is that F is proportional to Q1, Q2, and over R squared. So F is proportional to the product of the charges and inversely proportional to the square of the distance between them. So if you remove this sign of proportionality, you have a constant K. So that K is basically 1 over 4 pi epsilon naught. So this E naught is the permittivity of free space. Then, so since force is a vector, so the direction of this force depends on the sign on the charge. So don't forget that like charges will repel and unlike charges will attract. So for two particles A and B separated by some distance, they both exert equal but opposite force on each other, according to Newton's third law. So what does that mean? If I have two charges, so let's say I have a charge, a positive charge here, and I have a charge, another charge here. So this charge will exert a force on this. So let's say this is A and this is B. So A will be pushing B away. So that is a force that B will experience that force due to A. And A will be pushing B away. B will also be pushing A away. So that is the force. This is the force that B will experience due to A, and this is the force that A will experience due to B. So that is what is these two forces. If these charges are the same, they will be equal. Then, to calculate the force on a charged particle due to two or more other charged particles, we perform Coulomb's law calculation to work out each individual force. So we used the equation given before, and then the total force acting on one particle is then this vector sum. This is very important, of all the forces acting on it. So this makes use of the principle of superposition of forces and holds for any number of charged particles. So what do I mean? So let's say I have 4 charges. So let's say I have Q1 here, Q2 here, Q3 here, and Q4 here. So if all these charges, they are of the same magnitude, if I want to determine the force, let's say these are positive, for example, positive, positive, and positive. So if I put a positive test charge here to determine the force here, so this will repel that, F3 will go that way. And this will repel that, so F1 will go that way. Because this force, this positive test charge you bring will repel that one. So the force on this charge due to this is F1 and it goes that way. And the force on this charge due to this is that way. So if these charges are of the same magnitude, so this will cancel out. So the same thing here, the force on this due to this, F4 will point that way, and F2 will point that way. Sorry, F2 will point that way. So if these are equal as well, we will cancel out. And at the end of the day, the force on this will be 0. Okay? Then, if you have two charges like that, so let's say you have a charge here, Q1, and you have another charge here, Q2, then to calculate the force, so if you want to know the force on this, so you calculate the force due to this charge, you calculate the force due to that charge. So let's say you have a positive charge here. If this is negative, then it's going to be attractive, for example, it will go that way. and if this is, so the arrow will go that way, and if this is positive, as you know, and if this is negative, it will attract, and then the resultant will be calculated using Pythagoras theorem. Okay, so you calculate the force due to this, and you calculate the force due to that, and you find the result. Okay, then if you have these two charges, so let's say you want to determine the force, so you know you determine the force. Let's say you want to find the force at this point, explained by the charge that is placed here. So you need to calculate the force between these two charges. So let's say this is positive and this is positive is 1. This is charge 1, charge 2. If they are both positive, it's 2. If they are both positive, if I bring a positive test charge, so the force on this due to this will go that way. That's F1, and F2 will go that way. And then I can find the resultant. So F1 minus F2. Okay, so the direction in which the direction in which it moves depends on on which of the forces that is bigger. Then now electric field. So the electric field strength is the force acting per unit charge. So E is basically F over Q. And E is a vector, don't forget. It's a vector quantity, and direction of the vector is the direction of the Coulomb force acting on a positive charge, Q. So which means the direction of the field basically is the direction of the force. So, and to calculate the electric field strength is basically force per unit test charge. Don't forget per unit test charge. So the force between the charge and the test charge, remember, is Q test charge over, K, then R squared. So if you divide that by QT, then that cancels that, then you have that remaining. So that's how we got that. So electric field strength is proportional to 1 over R squared. So the separation distance R is, if the separation distance R is doubled, then E would decrease by a factor of 1 over 4. So that makes sense, because when you to R, if we square that, it becomes 4R squared. So we have 1 over 4 of the original E. Electric force F experienced by charge Q is given by F equals Q over E. So remember, F equals Q, E equals F over Q. So we make F the subject is going to be E multiplied by Q. So we see that this is of the same form as the relationship between gravitational field strength G and force. So if you compare that with that, then similar form. The only difference is that when you're looking at electric field, you are looking at Q. When you are looking at gravitational field, you are using M. So G is the gravitational field strength, E is the electric field strength. So that's the kind of similarity between them. So to determine the direction of the electric field at point X away from a point charge Q, so we place a positive test charge at point X and determine the direction in which the test charge will move due to its interaction with Q. So I've said before, so we always use a positive test charge in order to determine the direction of the field. So the direction in which that charge moves is the direction of the field. Then the electric field is a vector, as we know. We can calculate the total electric field due to more than one point by doing the same thing as we said before. So you have to calculate the electric field. If you put a positive test charge here, electric field due to that, then you will find the vector sum. So for this and for that as well, similar to what we did for force. Okay, now the electric potential. The electric potential tells us how much work is done in moving a unit positive charge when you place it in an electric field. Basically, the work done when you move a charge from a point to another point in an electric field. So usually we use infinity, that we bring the charge from infinity. So it means that the work done per unit charge is equal to V. So if you make work the subject, then W will be QV. So take note of that formula. Okay. So the potential difference, V, between 2 points A and B, separated by distance D, is the work done in moving one unit of charge 1 unit of positive charge between those 2 points. So if you have 2 points, you have like let's say parallel plates, negative, positive. So, and you have the distance d. So when you move a charge from a point to another point, so the work done in moving that charge from here to there is basically the electric potential if you have a unit charge, so 1 coulombs of charge, basically. So now remember, W is force times distance, and we know force is EQ. So force times distance, then you replace F with EQ, then we have EQ times D. Okay? So, and that is equal to QV. Don't forget work is that. So then we can cancel the Q. Then V will be ED. So you'll have seen this formula before. Now, note that the work done in moving from A to B is independent of the route taken. So that is, does not matter how we get to B from A. So the work done is always the same since the electric field is a conservative field. So that's the reason. So it means that if you move from this point, we are going from A to B. So if we go that way, so the work done is always the same, even if you go from this point to this point and then to that point. So it doesn't matter. What is important is the work done in moving from A to B, provided we move from A to B, will be the same, irrespective of the routes taken. Now, electric potential can be positive or negative, depending on whether the electric field is produced by a positive or negative charge. This is very important. Unlike gravitational field, which is always negative because it's attractive, remember, it is always a positive test charge that is brought from infinity to a point in the field. So if the charge producing the field is of the same polarity as the test charge, then the electric potential will be positive. So if there will be a repulsion between the charge that is producing the field and the charge that is brought from infinity, if they are of the same polarity, so they will repel. So when they repel, then the electric potential will be positive. And otherwise, it will be negative. So this is the formula. Electric potential is KQ over R. So remember, V equals ED. So which means ED is like a separation distance. So if you know, and E is what? KQ over R squared. So if you multiply by another R, so that will get rid of that. Then you're left with what? KQ over R. Unlike electric field strength, electric potential is proportional to 1 over R. So which means if I have a graph of V against R, so a graph of V against R, if it is positive, that is, if I have 2 charges of the same polarity, it's going to go like that. It can also be like that. So depending on whether the V is negative or positive. Okay, so it's proportional to 1 over R, unlike electric field. Now, to clarify the sign of electric potential, you take note of the following point. So if the electric field does work on the test charge, then the charge will gain electric potential energy. So potential will increase from infinity to that point R. Hence, electric potential will be positive. So this will be the case if you have the same polarity, for example, positive, positive, or negative, negative. So if work is done on the field, so remember here, the field does work on the charge, but now if the charge does work on the field, then the charge loses electric potential energy. So the potential energy will decrease from infinity to the point R. Hence, electric potential will be negative. So to summarize, all you need to note is that if there will be repulsion between the test charge and the charge that is creating the field, then electric potential will be positive, and if there will be attraction, so electric potential will be negative. That's the main point to remember. Note, for gravitational potential, the gravitational field does work on the mass. So when moved from infinity to a point in the field, so gravitational potential is always negative, okay? Because it's an attraction. There's always an attraction in the case of gravitational field. Now, electric potential is a scalar, unlike electric field strength or electric force, although the sign is determined by the sign of the charge. So the resultant potential due to multiple charges is calculated by scalar addition in this case, not vector addition, scalar addition. Note that electric field points from high to low potential. So electric field, we always point, or the electric field lines, we always point from high potential to low potential. So how does the graph of V look? So we've looked at that before, V against X. So it depends on against R, you can say R, the distance. So it depends on the nature, whether it's attractive or repulsive. So you can have it out. Okay. So because it's proportional to 1 over R. So 1 volt is equivalent to 1 joule per coulomb. So don't forget that potential is basically work per unit charge. Okay, so joules per coulomb. So this implies that if a charge particle moves through a potential difference of 1 volt, it will gain or lose. So depending on whether it's moving in the direction of the field or against it, it will gain or lose 1 joule of energy per coulomb. So the energy E gains by a particle of charge Q being accelerated through a potential V is basically E equals QV. So that's how to calculate the energy. So which is the same as work done. So this energy is equal to the kinetic energy of the charged particle. So the energy is equated to the kinetic energy. Okay. So for an electron, all you need to do is to replace Q with E. If you want, for example, you can use that to calculate the velocity of that moving particle, of that charged particle. Okay. Now, if a charged particle Q is placed in an electric field, it experiences an electric force in the direction of the field, and that force will cause it to accelerate. Okay. So the magnitude of the force experienced by that charge is equal to ma, according to Newton's second law. So if I make A the subject, I can calculate the acceleration. So the acceleration of that particle is basically EQ over m. So EQ is the electric force experienced by the charge, and that's equal to what? ma, and that's how we got that. So the direction in which the charge moves depends on its polarity. So the direction of the electric field is the direction in which positive charge will move. So that's how you figured out the direction in which that particle will move. So an electron will move in opposite direction. So if you have a positive charge, so it's going to move in the same direction. Is the direction in which a positive charge will move. So if it's let's say this is a positive charge. So if you have a positive charge brought near the field is going to move away that way. Or electron will move that way. So because there will be an attraction. So it is negatively charged. Okay. Then now let's consider an electron that enters an electric field at right angle to the field. So the motion of the electron is similar to that of a body projected horizontally. So why? Because that object will have two components to the motion. So, you project an object on the top of a cliff, for example, in a gravitational field. So the motion is like a parabola. So because there will be two components to the velocity. Okay, so it's similar to a charge that enters an electric field. Okay, so at right angle to the field, there is no force acting on the electron because the electron will move in the direction that is parallel to the field. It's either it moves, because an electron, so it's going to move if these negative plates, this will be positive, then the electron will move like that. So the electron, okay, this will be negative. Sorry, this should be negative. Positive, So the electron will move towards the positive plate. So it's going to be deflected like that. Okay. So in this direction, it's going to experience a force that is in the direction that is parallel to the field. But in the direction that is perpendicular to the field, it's not going to experience a force. It's going to move with constant, with uniform velocity in that direction. So you're going to move with uniform velocity in this direction, and it's going to experience a force in that direction. And the magnitude of that force is calculated using F equals QE. So similar to that. So now if a charge enters a uniform electric field, so the trajectory of the particle depends on the direction in which it enters. Yes. So if the charge enters parallel to the field, then the direction of the acceleration is parallel to the field, as in previous point raised in previous slide. However, if it enters perpendicular, then the direction is parabolic. So basically, if the field is that way, and the charge enters like that, and then it's going to move parallel depending on the direction, depending on the nature of the charge rather. But if it enters perpendicular, then its motion will be parabolic, that way or that way, depending on the nature of the charge. So consider a positive charge entering a uniform electric field created between two parallel plates. So here, positive and negative plates. So the trajectory is parabolic, as mentioned before. So this means that we can solve problems involving charged particles moving in an electric field in the same way we solve problems in kinematics. So remember, using the Schubert equation of motion. So in the direction perpendicular to the field, so which means looking at the horizontal component of motion, there is no acceleration, as mentioned before. And since the electron experiences no force in this direction. So in the direction parallel, so the force will be EQ, and we can equate it to MA, and we can find the acceleration using that. Now, to calculate the distance, y, so remember, so this is what we have. So it's going to, if I show you so to calculate this distance, y that is going to move, this distance, then we can use the equation of motion. So now I'm looking at it enters that way, then it's deflected, and we are calculating that distance, the deflection. So this is the length of the plate, the separation distance between the plates. Then we can use the Schubert to determine the time, basically the time of flight between the plates, how long it takes to move between these two plates. Once we get that, we can then use that time to calculate the distance using this equation again. So if you consider the horizontal component of the velocity, so since there is no acceleration in the horizontal direction, then this part will be 0. So then we are left with that part, and I can use that to determine t. It has a velocity in that direction. So because it enters with that. Then once I calculate the acceleration, I can use then S equals ut plus gravity squared again, but this time around, I'm using the vertical component of the velocity. So the vertical component of the velocity is 0 because when it enters horizontally, so it does not have a component for the velocity in the vertical direction. So this will be 0, and that part will be 0. So I'm left with the distance, which is now represented as y, will be equal to half at squared. I've calculated A before, previously, using S equals ut. I've calculated T before. So I can then use that T to work out Y, because I've also calculated A before. A is calculated using Q EQ over M. Okay, so with that, I can calculate the deflection because I know A, I know T. So that's how you can calculate that deflection. Okay, So charged particles moving in an electric field has application in cathode ray tubes, like example of the application, and particle accelerators, linear accelerators, and even Rutherford scattering experiment. I hope this summary is helpful. So there will be a calculation. I'll make another video to go through some examples using this concept that will explain. I hope you find this useful. So if you find this useful, please subscribe to my channel so that you can get notification of new videos. Thank you very much, and I'll see you in the next video. Bye-bye.